Hi, everybody. Thanks for joining. We're going to continue to let folks trickle in over the next minute or so, and then we will get started as soon as possible. Thanks. Okay, so we are at fully 2 minutes plus after the hour, so we're going to go ahead and get started. Welcome, everyone, to the ML FMEA virtual event. I am Jane Bailey with the Marketing and Comms team here at Torc, and we are so pleased that more than 500 of you, I think, took the time out of your day to join us here. So also joining me today are the authors of the paper that we're going to learn more about, and they are Paul Schmidt, Jerry Lopez, Bodo Seifert, and Christoph Pennar. So, as you may know, this paper was presented at the SAE World Congress in April of this year to great fanfare. Today, Paul's going to talk to us about the motivation and the reasoning behind the creation of the ML FMEA collaboration. And then afterwards, we're going to talk for about 30 minutes through a Q&A if you have any questions. Because we do have a lot of folks joining, we're going to ask that you use that Q&A function down at the bottom of your Zoom screen to ask questions along the way, and then we'll tackle those at the end. We'll be answering as many questions as we can, maybe live along the way as possible. If we don't get to your question either during the presentation or afterward, we'll follow up with published answers and send you a link. We'll also have a poll in the presentation. You'll find that function in Zoom as well when we get to that section. So just so you're aware, we are recording today's event, which we'll also share in the coming days, along with the presentation summary and how you can actually contact the paper's authors. So if you'd like to follow along in the presentation, you'll find the link to that in the chat function of Zoom, or you can find it on our website at torc.ai in the Knowledge Center section under Publications. So the authors have also asked us to note that they really intend this presentation and the associated template to be part of a larger conversation, and they really welcome and encourage your feedback and comments. So with that, I'm going to hand it over to Paul Schmidt.
Thank you, Jane. Thank you so much. It's thrilled and an honor to be here on behalf of all the co-authors here. We're just excited to present the material and really excited on the popularity of the topic. To get things started, we'll do a short introduction of the co-authors and the presenters here. Yeah, my name is Paul Schmidt. I'm an autonomy software senior manager with Torc, and I'll pass it over to you, Bodo.
Yeah, my name is Bodo Seifert. I'm working as the senior safety lead for TÜV Rheinland here in the United States. Used to work with Paul and the gang at Torc Robotics until about a year ago, but yeah, now I'm working for TÜV, and then I guess I can hand it over to Jerry.
Thanks, Bodo. Hello, my name is Jerry Lopez. I'm a senior director of safety assurance here at Torc. And I also spent 2 years at a robotaxi company. And just very briefly, my team is responsible for ensuring that our system exhibits safe driving behaviors and collision avoidance. And clearly, ML safety is a big contributor to that. So delighted to be part of this presentation and this talk. Thanks.
And Christoph, please.
Good afternoon, everyone. Thanks for being here and a part of this talk. My name is Christoph Pennar. I'm a principal safety engineer at Torc, and I am helping lead our AI safety strategy.
All right, wonderful. Thanks, guys. All right, just a quick housekeeping note. I'll be doing the lion's share of the presentation, but I'm inviting Jerry, Christoph, and Bodo to add color and comments, you know, to jump in the middle of the presentation wherever And also, we're really looking forward to the Q&A at the end, where Jerry and Christoph and Bodo will absolutely be essential. As Jane mentioned, this material that we're presenting was published at the SAE World Congress. And it's really due to the popularity of that presentation and the response afterwards that really motivated us to host this virtual event. So tip of the hat to TUV Rhineland and to Torc for hosting this and doing all the behind the scenes work. It's much appreciated. And as Jane mentioned, there's a link in the chat to the paper, to the material that we're about to present, both the SAE paper as well as the preprint. So feel free. Okay, so with that, let's dig in. So we're structuring the talk here in these main categories. First, we'll talk about the motivation. Why did we get into this topic? And then laying the foundation here. There's just a couple of key concepts that we need to share, and that'll really set us up for success in describing the ML-FMEA method, as well as the ML-FMEA template. And we're very happy and proud to say that we've been able to make it open source, and so we've got some information to share there as well. So let's jump into the motivation. So I think for the vast majority here of the attendees, I think you'll appreciate that machine learning models are highly complex. They're black box, non-transparent in terms of the decisions that they're making, and honestly, interpretability and explainability is very much an active area of research today. So this really challenges traditional safety analyses. Most safety analyses today are that related to software, are dependent upon the software being very highly deterministic. Another key motivation was if we look at the state of the art, very happy to say that there are several current and upcoming standards within the space of machine learning or artificial intelligence and safety critical applications. We can think of ISO 5469, the recently published ISO PAS 8800, to a lesser extent, UL 4600, ISO 21448. But these standards, what we've found is that they reference that there's a need to systematically ensure the safety of the machine learning model. But we felt that there wasn't enough prescription, there wasn't enough direction for the development teams. And so we felt that there was a gap, really an opportunity for a specific technique and methodology. Ideally, this technique, this approach would be holistic to address all ML engineering and V&V activities. It would help indicate the needed level of rigor to the team and the focus areas. And it would support an overall safety argument, providing sufficient evidence and support the argument that the ML algorithm is absent of unreasonable risk. So that really, in a nutshell, was what motivated us. And so next, I'm going to talk about the contribution. What do we feel that this paper, this material is how it's advancing the field? We feel that we're contributing two pieces here. The first is the ML-FMEA, the method, which I'll get into the specifics in later slides, but the high-level overview is it connects the ML pipeline step with relevant failure modes, and connects those with causes, and connects those with known ML mitigations. Again, I'll get into the details here in a bit. The other contribution that we feel that we're making is the template. This is PFMEA modified for machine learning. It's pre-populated, and we feel it really enables ML developers to assess, prioritize, and communicate safety risk. Again, I'll get into the details in these two in a little bit, but just wanted to provide an overview. Okay, so now to help us understand the method and the template, we're going to lay the foundation, talk about just two key concepts. And first concept is the ML, the machine learning pipeline. there are several popular ML pipelines that are out there in the literature. This is one that we crafted for the paper. We worded each step in a special way so that it was very clear, but also showed the value that was being added into the process. And so it's set up as a value-added process. And so I'm splashing this on the screen, and what I thought I'd do is just like dip our toes briefly into each one of these steps, just so that you get a feel for the ML pipeline. The first step here is the collect data requests. And what's happening here is the team is defining the problem to be solved. What is the problem that we need to solve, and what is the data that we feel that's needed in order to solve that problem, the data that's needed for the ML model. So we collect what all those data requests and submit those, and usually that goes to a different team. And here in step 2, we're collecting the data, and there's, at least in our industry, there's a data collection team, and usually there's multiple platforms, many different types of data that's being collected by different teams. So that needs to be managed and acted. So that's step number 2. Step number 3, we're ingesting the data. So again, the data is coming from different platforms, different teams at different times. We need a way to ingest the data into one area, typically the cloud environment, at least in our industry. Step number 4, validate the data. It's a key step here to see what gaps there are in the data, perhaps missing time steps, ensure that it was the right protocol for the data followed. Was there a dirty sensor on that day, perhaps? Step number 5, pre-process data. This is a key step to get the data ready for training. And typically here we're normalizing or scaling, or in the industry, squashing the data. And then step number 6, before we train the model, we actually need to select the type of model and the algorithm that we're using, and then actually train the model itself. And step number 7, we're adjusting the hyperparameters of the model. And step number 8, analyzing the model. So going back, in step number 1, we define the problem. Is the model now solving that problem? So we're analyzing the model. But typically this is, at least in our industry, in the cloud environment. And so we need to actually, step number 9, deploy the model into its intended application, typically onto the processor, which will have specific processing constraints. So we're rescoping, reshaping the model for that environment. And then step number 10, since we have a new model, does it still giving us the performance needed to solve that problem? So in step number 10, we're validating the model before we deploy it into the field. And then step number 11, we're analyzing the model feedback as it's being used out in the field. So I know that was a breezy, quick tour through the ML pipeline, but just wanted to give you a sense of what, the value that's being added here in each step. And so this is the first concept, the ML pipeline. The other concept that we want to share here, provide at least a basic understanding, is the process, failure mode, and effects analysis, or the PFMEA. This is not a presentation on what a PFMEA is. I mean, there's lots of other much better materials out there, but just to give you a sense for what it is, if you're not aware, it's an established, structured method for identifying and mitigating potential process failures before they impact quality or safety. I'm not a historian, but I believe it first got started within the automotive industry, specifically for manufacturing processes. But over the decades, it's been cascaded and used across numerous industries, I know, for numerous different processes. And a key aspect of it is that it assesses failures for each step in 3 key dimensions: and the severity of that failure mode, estimated occurrence, and the detectability of detecting of that failure mode. And so it's a tool that really enables the design teams to identify, prioritize, and manage safety risk. So that's the second key concept that's employed here, and that sets us up to help explain the MLFMEA, the method. All right, so for the method, the key concept here is really that the method views the ML pipeline as a process, as a value-added process. And so the model, the ML model itself, is then an output, or it's a byproduct of that process. So the idea is that if we have a quality process, we'll have a quality model. And so the method itself, it starts with looking at the ML, the value function. So what value is being added into each step, and then looks at the failure mode, that all the possible failure modes of that function. And then it looks at all the possible causes of those failure modes, and then connects known ML best practices and mitigations to address those causes. So that's a breezy look. To help it feel a bit more concrete, what we'll do here for the next couple minutes is I'm just going to pick a few of these steps and give a few examples of the method. So I'll start here with step number 4, validate data. If you remember what's happening here, what's the value that's being added in this step, it verifies that the collected data meets quality standards and is suitable for analysis. So again, we're collecting all that. We've collected all the data from the various sources, but we need to make sure that it's not missing data. It's in good has a strong protocol, so it's suitable for the next step for pre-processing. So it ensures the data is accurate, complete, and free from significant errors. Okay, so this is the step. So now an example of a failure mode from the paper is invalid or corrupt data can lead to erroneous model training and predictions. So a possible mitigation that, again, that we list in the paper is schema validation. This is not something that we put forth, but it's readily available in the ML literature. What is schema validation? Enforces data structure and type constraints through schema definitions, and there's several tools. So basically, there's a protocol that's expected, and we run a tool to check that protocol is being followed. Okay, let me jump forward to step number 6 here, where we're training the model. What's happening here? This is where the teams are selecting the appropriate algorithms, they're configuring the model parameters, and fitting the model to the training data. And then training the model. So I've got a few examples of some possible failure modes and causes here. The first one's incorrect algorithm selection can lead to poor model performance. Incorrect algorithm selection. So possible mitigations include, well, ensure the understanding of the problem that's being solved. So did the team really do a good job back in step number 1 of identifying the problem that needs to be solved? Because there's some models that are better for certain problems than others. Another possible mitigation here, number 2, clarify and document available data characteristics. Depending what that means is depending upon the type of data that's gathered and available, certain models lend themselves better to certain types of data. And the third one, employ multiple models. So if the team feels that there's 2 or 3 models that might perform well, let's employ those 2 or 3 models, and then use a consistent training pipeline across those and compare the results using a cross-validation technique. Okay, so that's potential failure mode 1. Let's just stay here on this step for a little bit. And potential failure mode 2 that we list is overfitting or underfitting the data. So possible mitigation is cross-validation. So we can employ a well-known technique, k-fold cross-validation, to check the model's consistency across different data subsets. So we break the data up into different subsets and employ the k-fold to and evaluate the level of overfitting and underfitting. Okay, so that's step number 6, and then I'll pick one more step here. Step number 9, deploy model. And if you remember, the value that's being added here is this is where we're taking the model, at least in our industry, we're taking the model from the cloud environment and deploying it into the production environment. Oops, sorry. And we're checking the reliability and efficiency of the model as it's performing in that production environment, that typically that hardware processing environment. Okay. All right, Kylie, I'm having trouble clicking forward to the next slide. If you can help me. Okay. All right, thank you. So a possible potential failure mode here in the deploy the model is inadequate infrastructure can lead to performance bottlenecks. What do we mean here, the inadequate infrastructure? So this is things like memory or processing capability. So we're deployed onto the hardware, onto the chip or board itself. And also remember, we're coming from the cloud environment where perhaps the model may have near infinite memory resources or processing resources. Now those are limited. So that's a potential failure mode. So possible mitigation is we can employ a continuous integration, continuous deployment check. We implement a pipeline check to automate the deployment process. CI/CD ensures smooth updates that minimize manual errors, preventing deployment failures and maintaining model consistency. So we employ an automated check before we release the model to ensure that it's the estimated memory and processing that it requires fits within the constraints. All right, and I think I've got one more. We'll stay here on step number 9, deploy model. Another potential failure mode is poor monitoring can result in undetected performance degradation. So have we really thought about the metrics and the data that we want to pull out of that production environment to give us a signal, to give us a clue that it's performing well? So possible mitigations include logging, continuously monitor the deployed model's performance and log predictions. And then if we know the metrics, perhaps we can set up some thresholds for those metrics and trigger some alerts. So set up alerts and to have that information jump off the page of the logs. Okay, that was, again, a breezy look. Just grabbed a few of the steps of the pipeline and gave a few examples of some failure modes and some mitigations that are directly connect to those failure modes to give you a sense for the ML FMEA method. Okay, so now moving from the method to the template, the ML FMEA template. So what is this? So this is where we've taken the PFMEA template, a typical PFMEA template that you can download off of the internet, and we tailored it for machine learning for this application. Want to state up front that most of the columns of the PFMEA we felt did not need to change. They are very much in common with what, if you've worked with a PFMEA before, it would be very familiar to you. But we did feel that, multiple columns in common with the PFMEA template. But we did feel that 4 columns in particular should be modified or tweaked. The first one is the first column, the pipeline step. Within a PFMEA, this is typically called the process step. We're changing that to the ML pipeline step for clarity. The second column that we changed was the failure mode column. And we clarified that this is the failure mode of the ML model of interest. So that's our system of interest here that we're drawing the dotted line around. The third column that we changed was the cause column. So clarifying that's the potential ML pipeline cause. And then the last column was the mitigations column. We're calling this the ML pipeline best practice and process control. And we pre-populated the template. So we feel this is really the power of the template, is that we listed all of the ML pipeline steps. We listed all of the failure modes, the permutations and combinations of the failure modes that we could come up with. And we listed all the potential causes of those failure modes that we could come up with. And then for each cause, we identified a mitigation, at least one mitigation. Sometimes I think we had 5 or 7. And I'll splash this here up on the screen not to read every word, of course, but to give you a sense of the depth here of the material within the template that would be available to the ML development teams and safety assessors. Okay, so that just provides an overview of the ML FMEA method and the template. And again, like I mentioned earlier, we're so happy to say that we've made it open source. So in that same link that's in the chat, you should be able to find the link that takes you to the open source, to the GitHub repository, where it's available right now on github.com. And we're really excited to invite the community to use and improve the template across industries. We want to be upfront and honest. We don't feel that we have all the answers for all the different industries out there. And that's really exciting to us. We feel that really, I think our theory is that there was a different unique ML pipeline for each different industry and each different company or different research team and so on. So really, again, excited to get this information out there and really hope to advance the field. Okay, so we just got 2 more sections left to cover, but we thought we'd take a quick time out here and open it up to a poll. We're just thrilled to look at the registrants and see the registrants coming from seemingly all around the globe, from North America, Europe, and Asia, but also across industries, public policy, and the research community. And so I think what we'd like to do, hopefully there's a poll question popping up on your screen. If you wouldn't mind just selecting, the area of your perspective, where you're coming from, that most resonates with you. And we're just really curious to see, because again, we saw that from the registration list, people not just from our industry, the autonomous vehicle industry, but also automotive, energy, entertainment, medical, defense, aerospace, and also from research fields, public policy, and the standards community. So appreciate if you just would select, perhaps you already have in the time that I've covered it. Okay, thank you very much for filling that out. Now getting, again, just a couple more sections left. So discussion section here on the benefits and the limitations that we see to this approach. And I'll start actually with the limitations, just to be upfront and clear that we do not view the ML FMEA as a standalone safety tool. No, rather we see this part of a more comprehensive safety management system. And really, if your team uses safety cases, it can be a a powerful key component or an artifact of an overall larger safety case. So having said that, what are some of the benefits that we feel that the method provides? Well, several. The first one, basic one, is it provides development teams a systematic way of identifying and documenting functional insufficiencies and mitigations associated with the ML pipeline. And we feel that it can be used as a checklist to ensure that no critical steps were missed in the ML pipeline development. You can see the template there to the left. It gives them a list of, okay, did we include this step? Have we thought about this potential cause? Another benefit is it helps to identify steps in the ML pipeline that could have the highest impact on safety risk. Again, the PFMEA enables prioritization of safety risk, and so this it's a key benefit to highlight those are the biggest areas to focus our limited resources on. Number 4, can serve as an important evidence artifact supporting a safety case claim that the ML pipeline was developed with the highest level of rigor. And then my favorite one, number 5 here, is we feel that it enables a common language between the ML development teams and safety assessors. And in my experience, those are two very different teams, the ML development teams and safety assessors. They have different backgrounds and different vocabulary. I've often seen them talk past each other. So this, really provides that common language, common focus areas. Okay, so that's the benefits and limitations. And now just a few thoughts on future work that we're really excited about. The first one is going from concept to application. So as you go through the paper, you'll see that the paper is really conceptual. And we're really excited to apply these concepts to actual real life applications, actual real models that are being designed and developed for safety critical applications. So within my company, within Torc, we've been working on the proof of concept, applying this to a model for the last several months. And one thing, and we want to highlight also, we are now forming the ML FMEA collaborative. We're, inspired, by the interest to this approach. And so within this collaborative, we've envisioned that we would share and compare notes, share the learnings of applying the method to an actual real life application, because that's really where the rubber meets the road and unleashes the power of the approach. And the intent is that we would publish findings and results. Of course, the intent is that, as we share and compare notes, we would do it at a high level so as to, steer clear of any potential, IP issues or that kind of thing. So if you think that your organization may be interested in participating in the collaborative, feel free to reach out to one of the co-authors. Another thing that we're really excited about going forward is the open source community improvements. Really excited to see the community take ownership of it and see how it branches, branches in the different flavors that it branches off into to make the most sense for the different industries and applications. Okay, so to summarize, we have presented the ML FMEA method, which analyzes safety risk at each stage of the ML pipeline. It's based upon proven failure mode analysis and ML methods. And we've presented the ML FMEA template, which collects ML development pipeline failure modes with machine learning best practices as mitigations, and enables ML developers to assess, prioritize, and communicate safety risk, and really empowers safety assessors to ask the right questions. And it's designed to help with analyzing ML models in safety critical applications across automotive, autonomous vehicles, military, aerospace, medical, pharmaceutical, energy, entertainment industries, we feel. So thank you very much for attending. And on behalf of the co-authors, we're thrilled that you're here and really looking forward to the questions and answers. So Kylie, I'll turn control back to you.
Thank you, Paul. I am going to be a bit of a floating head in the background, and I'm going to stop sharing for a moment, and we are going to highlight our people who are the co-authors who are going to be answering the questions that everyone has been putting into our Q&A. And also there's a few in chat that I'll read out as well. But we have everybody here who can answer the questions. And I'm going to start with just a couple of ones that are in the chat, and then we'll move to the Q&A. If we don't get to everybody's question, we will be doing a transcript and filling in answers that we don't get to. Those will be available on the event page. We'll be sending out a link to that by the end of the week. Okay, so the first question that we have is, how do you ensure coverage for unknown unknowns, especially in perception ML systems using this method?
I know I've been doing the lion's share of the talking, so happy to pass it over to one of my co-authors if you'd like. Or
yeah, so I'll take a crack at that. I think you're referring to the ISO 21448 standard. I think it's Area 3, unknown unknowns. So this technique does not claim to be like the silver bullet that's going to answer all of the unknown unknowns. And to Paul's earlier point, it's one tool among many that can be used. But I think formalizing a process where you look at each process step in the ML pipeline development, it helps you to sort of brainstorm and elicit with a team of experts on what are some of the things that could potentially go wrong with a particular step or steps in the process that could, and then also connecting that to how those process defects could manifest themselves, at runtime when you're operating the machine learning model in the actual world. So, there is potential to be able to elicit some of those, things that you hadn't thought about before about how process defects might manifest themselves. But again, it's one of many tools that could be used to help, elicit the unknown unknowns.
Okay, next question we have are, what are the challenges to scaling this process to an integrated FMEA?
So I guess I don't understand. I don't know if the other panelists, but what is meant by an integrated FMEA?
I guess maybe one question that could be answered is, I mean, in the end, what we will have to do in order to achieve functional safety for something like that is, I mean, we would start with a system level FMEA, and then we break it down into hardware and software related FMEAs during the process. And if the question were how to integrate that, then my answer would be what Paul has shown in the presentation is probably at the system level. So, I mean, we are talking about how we are analyzing certain things like maybe the data capture, how is that going to work? Then some of these methods could be model agnostic, but then later on you'll have to break it down for the specific implementation that you're doing that. But the nice thing about an FMEA in general is that you can start pretty high level and then you break it down. But in the end, it needs to be understood. An FMEA is always a bottom-up methodology in compared to an FTA, which is top down. And so you got to understand what level you're on, and then basically make sure that the expectations are clear when you start.
Yeah, absolutely. I totally agree, Bodo. If that was the intent of the integrated FMEA, this FMEA would fit in within the larger, structure of the system FMEA, where, that's where the severity numbers come from, right? The severity numbers cascade down, the occurrence numbers, cascade up, if I can use that term. So it still fits within the typical FMEA structure.
And someone just added a clarification on that, and it had something to do with the, I'm just reading it here on the, it's integrating process design and tool FMEA together as one example of integrated FMEA. Well, I mean, one thing I'll say about that is, again, the purpose, one of the purposes of the development of the process FMEA, some time ago, was to identify defects in the process and then close the loop on improving the process so that you minimize the number of defects that are allowed to go out into the field. So there's definitely a strong link between this FMEA construct and improving the process and improving the process design.
Yeah, I think I would just also add that what's unique here is that an AI algorithm includes a data component, right? A data set component. And you really scratch the surface of that with a process FMEA type approach, and you're able to dive into what is the process for obtaining that data for your ML model training. So by having the FMEA approach or process FMEA approach, you're able to gain insights into exactly what's that process for generating that data and then using that data for training and then evaluating prior to deployment. So it serves as a bit of I would call it almost a prerequisite to any SOTIF work or anything like that I noticed in some of the other questions.
Okay, we're going to move on to another question. This one's actually from Axel Gurn, which is a name that many of our panelists are familiar with. He says, thanks for sharing. I like the structured approach. What I am missing is how SOTIF is addressed, e.g. due to hallucination of the model? Question mark.
Maybe I'll continue on this, Axel, because I think I was actually looking at your question here and starting to formulate my prior answer. So it's a good question, but I think what we've been seeing across the industry, right, is that AI safety is developing as its own component and its own pillar, independent of SOTIF. With SOTIF, you do have your functional limitations and triggering conditions, and you need to have an accurate accounting of those. And just like how you have a functional limitation, for example, on your radar range, you also have functional limitations of what your AI can do in terms of how it's classifying things and what it's classifying. So you have that part, but we're asking the question of how do you create an ML algorithm that is safe, that then subsequently when you put it up in the vehicle level, you can start to see, oh, perhaps I have at an integrated vehicle level, I have certain triggering conditions that now may be visible, that previously are kind of emerging or that wouldn't have emerged at more of a integrated vehicle level. Much like how you have software safety that's applied to other types of areas within your software stack. This is a safety method that is applied towards your AI elements of your software that then kind of come together, that then your residual that you're finding out from those unknown unknowns as part of your SOTIF analysis should start out being really minimized. And I think on top of that, and I've seen certain SOTIF analysis that try to get at this absent of an AI safety framework. You might have a mitigation that says, well, you need to improve your training data. But that might not necessarily be what you need to do. Perhaps you have the right training data, but It was a series of annotation errors that were systematic that are now uncovered through the process pipeline. So I think it does it can give you that additional insight when you allocate a potential triggering condition and you allocate it down to an AI element. Then you could dive deeper with something like this and say, okay, where in that process, and not just maybe saying I had insufficient training data. So I think it gives you more context around what that failure mode could have actually been that then spawned that triggering condition.
And maybe let me add one sentence to that, since I'm a stickler for standards, and so we mentioned ISO TR 5469. That one actually does mention things that the SOTIF standard 21448 would not mention. So SOTIF basically considers misuse, but it doesn't consider misuse that involves actual changing of the system. So if you basically modify your self-driving car by hooking 2 Coke cans to the steering wheel so that the driver, the method that detects that the driver has the hands on the steering wheel isn't working anymore, that's something that wouldn't be covered by SOTIF. So that's beyond that. But then the emerging AI standards now, they are actually looking at this. And then an example would be when you're trying to fool your AI by basically doing adversarial attacks to AI. And that's something that's new and that the standards are covering, that are coming out. And again, one of the methods that would be used for this is, hey, we could use a process FMEA to finally detect that somebody might have messed with our annotation methods that we are using. So maybe somebody is annotating images incorrectly, so that in the end we get unexpected behavior. Well, and then that would be something that would be covered with this emerging framework of standards.
Okay, thank you. Moving along, I'm going to start working, since we have about 12 minutes left until the top of the hour. I'm going to go on upvotes now. So if there's anything in the Q&A that you would like to see answered live, please go ahead and upvote those as you see fit. Our next question is, interesting application, seems to make some sense. Where is the risk identified effect of the FM? Secondly, how do you justify the quote mitigations and their value compared to the level of unreasonable risk? How is the unreasonable risk measured and classified?
I could maybe get started with this. I mean, people shouldn't take this process FMEA as an isolated silver bullet for everything. I mean, we got to understand that all the functional safety mechanisms and processes that we have in place still apply. And so, I mean, if you do this isolated without doing a hazard and risk analysis, then that would be problematic. And me as a safety assessor wouldn't be happy when you did that. So basically what you have to do is you still have to do the regular process steps that you're doing, like in the automotive functional safety. You have to define your item, you have to do your hazard risk analysis, and then basically you take it from there. So at that point in time, we need to understand the type of rigor that we have to do for a certain hazard. And this FMEA here doesn't replace all that. It's basically an additional tool to address the additional things we would have to do in order to make AI usable in standards like 26262, but also if you go into the process area, I think I've seen somebody asking for ISO 13849, or if you have an application that's EN 61548. I mean, all these standards basically require you to do a hazard and risk analysis, a formal one first, and I mean that's not replaced by this.
I would just add to that. I totally agree, Bodo, with what you said. But one thing that Paul talked about towards the end of the talk that this method does. So again, it helps you to identify potential failure modes with one of the process steps. But then it also connects that to expected severity or estimated severity, detectability, exposure, those sorts of things. And that turns into what we call an RPN number. But that has some indication of the level of risk, okay, the level of estimated risk. And again, that can sort of also be used in conjunction with the methodologies like hazard analysis, risk assessment that Bodo was talking about. So there is some construct in there that allows you to at least estimate the level of risk and compare, does one defect expect to be riskier than another based on those RPN scores. So there is something built in there for that. But again, it doesn't replace, by no means replaces the things that Bodo was talking about.
Okay, next question. What criteria do you use to assess the quote rigor of mitigation strategies in the ML FMEA?
Yeah, again, I'll get going here on this if you guys don't mind. I mean, these are two different questions. I mean, so we basically doing the steps that we talked about a minute ago, doing our item definition, our HARA, that gives us our ASILs or SILs if we are in the industrial area. And then that is basically what's driving the overall rigor that we have to do to implement the safety mechanisms that are being identified here. What we've seen with the FMEA methods here and the process FMEA, we would have to then understand and gauge whether like, for example, if I have an ASIL-D safety goal and I'm using the process FMEA as discussed today in order to mitigate that, then we would have to understand, is this really something that is sufficient? Let's use the example of ASIL-D. I mean, at that point, we need to get to 10 fit for the system, the safety goal in that consideration here. And then can we achieve that with the process FMEA? So that would mean, once again, I'm making these numbers up. If you have 1,000 images and you need to make sure that all these images are correct, well, then based on the 10 fit, you could then calculate for the key performance indicators that you're getting out of the safety criteria. Oh, and then you would have to make sure that your method will actually fulfill that. But the PFMEA itself isn't going to help you with the rigor. I mean, that's something that you would have to define, at least in my opinion, high up on the system.
Okay, I think we have time for about one more question. But before I get to that, I just want one quick comment from the chat if you guys didn't see it. There are conversations all around on AI evals focused on LLM evaluation, but this is by far best full coverage FMEA for ML I have seen. Thanks for sharing. So there you go, guys. Little shout out in the chat. So one more question. In your introduction, Paul noted that this ML PFMEA approach supports safety argumentation. Could you please elaborate on this point a bit? How do the results of this inform the preparation of a safety case?
Yeah, I can take this one on here. So when we start with a safety argument, we're trying to make an overall argument that our system is sufficiently safe, and then we start to decompose that. And we want claims that are substantiated by evidence. And within each claim that's substantiated by evidence, we have to satisfy that both with the evidence piece, but also with the process that led to develop that evidence piece. So if we have a claim that says that drills down and talks about the AI algorithm being sufficiently safe, then we have two components of that. We might have a regular VNV that might involve things like simulation and closed course and exposure on the public road, all to give us this sense of confidence. But I need to answer a second question, which is the process by which I generated the AI sufficiently safe? And ergo, you have the ML FMEA, and that would fit really nicely in an argumentation structure.
And I'll put one on top of that. The standard that we mentioned here, the TR 5469, that basically tells you what you need to do is you need to basically look at your 3 stages of your AI system. We did that today with the process description that Paul had. And then based on that, you have 6 properties that you're supposed to be using. And out of these 6 properties, you get methods and techniques. And then the PFMEA would be one of these methods or techniques that you're supposed to be using for that. And then that in the end builds your safety argument at the bottom, because it allows you, based on that, to say, well, this is the criteria that we're using. Either we reach these criteria and then that's our argument that we are safe, or we don't reach them, and then that means we need to do some additional things. So it's basically, it's a key thing, like what Christoph said, that has to be done if you want to make your safety argument using AI or ML.
Okay, everyone, we have about 4 more minutes. Do you think you can do one more question?
Yeah, and if I could maybe propose, I really like the question from Majed. If we could maybe promote that one, Kylie.
Sure. Let's see. We're going to answer this one live. How can this method be used to meet the EU AI Act that an AI risk management system is needed for high-risk systems?
Yeah, I know I promoted that question. I don't have the answer to that because I'm not aware, not familiar with the EU AI Act myself, but I don't know if Bodo, Christoph, Jerry, or you are. If not, I'm eager to dig into it.
My guess is that Bodo has more familiarity with that EU Act than the rest of us.
I'll take a quick stab at it. So yeah, the answer is a clear yes. So I mean, the European AI Act is something that basically tells you, hey, I mean, you gotta make sure that your AI system falls into 3 categories. Category 1 is an absolute no-no when you're trying to manipulate people. Well, this isn't something that we were discussing here for autonomous vehicles. But then the second criterion is really, I mean, if you basically use AI and then it can have an impact on safety, then you actually have to show that you're doing your due diligence in order to then ensure that functional safety is considered. And by basically using frameworks like what Paul had initially on the slides, like the emerging ISO 22440, or if you're using ISO Pass 8800, 8800, yeah. So that's exactly the thing that you need to do. But as Paul very eloquently said at the beginning of this, well, these standards really, I mean, they just tell you what to do, but really not exactly how to do that. And basically by showing what we've done here today by using a process FMEA, that's a good way of doing this. Like I said, this isn't a silver bullet, so there's going to be lots of other things that can be done and already basically state of the art right now. But at least, well, we are giving you a couple more tools in your toolkit here to do this.
Okay, with that, everybody, we are at close enough time where I'm going to do one more quick share on here. This is everybody's, the 4 individuals who have been with us today answering questions and presenting their contact information. Again, everybody's contact information is at the publication page. Again, you'll find that link in the chat. As Paul mentioned, they are looking for people to join the collaborative. If you are interested in doing so, please reach out to one and or all of them, and you too can be part of moving this hopefully new industry standard forward. So on behalf of everybody at Torc, I'd like to thank everyone for attending today. We really we're excited to see where this goes in the future. We will be doing a follow-up with this because it has been such a popular topic. So be on the lookout for more information from Torc and also TUV Rhineland. We'll be doing another of these going forward. And again, this recording of this webinar will be available on the event page by the end of the week. So look for another email from us at Torc. And with that, we'll sign off for the day. Have a great rest of the week, everybody, and we appreciate your time today.
Thank you. Thank you so much.
Hey guys, thanks.
Okay.